This section is discussing how to find the area between two curves. So we can easily extend the concept of finding the area under a curve to finding the area between two curves. And that's what we'll do within the next lesson. But to get us started, let's review what it means to find the area under a curve. So for example, to find the area under the curve y equals 4x minus x squared on an interval, we always have to have an interval, we would use vertical rectangles trapped between the x-axis and f of x. Okay, so for instance, here's the function y equals 4x minus x squared. And if we're on the interval from 0 to 4, let's first recall what that means. So that means an interval on the x-axis, which begins at 0. Because I have this bracket, I'm including the 0, so x is greater than or equal to 0 and less than or equal to 4. This effectively gives us two vertical lines. And I know that they're vertical lines because the equations, well, inequalities, look like this. So x must be greater than or equal to 0 and x must be less than or equal to 4. But this sort of looks like x equals 0 and x equals 4. And x equals 0 is just a vertical line right here along the y-axis. And x equals 4 is just a vertical line right here along the, this vertical line, x equals 4. Now, that basically tells us where to begin and end this process. Now, very often the process just kind of ends where we start at the x-axis and then the function comes back and ends at the x-axis. But that's not necessarily have to be the case. Like I could have integrated up to just x equals 2 and then everything stops when I reach this particular vertical line. And what I end up with is the area up to that particular point. Okay, let's get back to the example we're working here. Now, in order to come up with this area, we used integration and the fundamental theorem of calculus. And we'll get to that as a review, but I just want to make sure everybody's on the same page as to how we come up with that approximation in the first place. So, I've drawn here an approximating rectangle, and I've only drawn one, but it's sort of inherent here that there's actually a whole bunch of approximating rectangles, a big series of them, and that series of rectangles allows us to very easily compute the area of an approximate area of this region. Because if we don't know the geometry involved in calculating the area of a region like this, then the best thing that we can do is use approximations based off of geometrical shapes that we do already know. So that's why we're using rectangles, because the area of a rectangle we just simply know is whatever its width is multiplied by its height. And we can get the width and height from measurements along the x and the y-axis, and the y-axis, of course, coming from the function itself. So coming up with the area of these individual rectangles one by one, then adding them all together, gives us an approximation to the total area under the curve. Now, obviously, there's a little bit of error in this process. So there is too much area here, and so forth. So there's a little bit of overage in each of these. And then also over here, there's a little bit of overage in each one of these, and sometimes it can be an over approximation, sometimes it can be an under approximation, just depending on where the endpoint of your rectangle is going to be. But regardless, there's some sort of error. using a rectangle to approximate the area of a curve. And you can get better approximations if you use different types of approximating methods, but ultimately there's some error involved. What we can do, however, is minimize that error by increasing the number of rectangles. So if we increase the number of rectangles, then that's going to decrease the width of each rectangle. So each rectangle then becomes even smaller. Let me just erase a couple of these so I can show you what I mean. So as the rectangles become smaller, then that extra amount that goes above the curve reduces. And therefore, we get a better approximation. So the more rectangles we use, the better the approximation ultimately becomes. Until we get to the point where we've used so many rectangles that we can't fit any more in there, and we end up with basically the exact area under the curve. Now, we don't really get the exact area under the curve, but we do get a limit that tells us what that exact area should be. And that's the value of the integral. So, let's take another look at how we come up with that value. All right, let me get rid of all this that I've drawn in here. None of this is really necessary. I just want you to understand that this one rectangle that I'm drawing is just a simplification of illustrating all the rectangles that exist. Now, when we were determining the area of this region, we used the height of that rectangle as our approximation. And the height of that rectangle could be computed by finding, ultimately, distance. So we have the top of this rectangle and the bottom of this rectangle, and the distance between the top and the bottom, and that's a vertical distance, so y2 minus y1 tells me the height of that particular rectangle. And this is just calculating distance in a single dimension. So if we just subtract two numbers, that's exactly what we're doing. We're calculating distance in a single dimension. Now, the height of this rectangle is defined by the function itself. So if I say that this is equal to some f of x, then the height of the rectangle is defined by f of x. So I could further improve upon determining what this distance is by, instead of using y2, I could use whatever f of x is. Now, the bottom of the rectangle is important as well when calculating this distance. It just so happens that the bottom of the rectangle is always located at the exact same spot. It's right on the x-axis, which means it has a y value of 0. It's just sliding along the line y equals 0. And if that's the case, that's ultimately a function. It's just a function that always equals 0. So I could substitute in that here, and obviously f of x minus 0 is always going to be f of x. So we've really just simplified how we are finding height by using only the height of the function at any particular point. And that's how we came up with the rectangular approximation. The x-axis was just used as a lower bound in approximating the rectangle. So let me write that out. So the x-axis was used as a lower bound for approximating rectangles. Now, with that, we've come up with this region, which has really four separate bounds here. It has a left bound and a right bound along the x that was determined by our interval. Now it has an upper bound, which is the function itself, and a lower bound, which is always just y equals 0, the x-axis. So we've really kind of sectioned off some region. All right, so we've really bounded some region here like this. All right, and within the bounds of this region is the area that we're trying to come up with. And the integral is going to do that for us. So just as a quick reminder, let's actually go through the computation of calculating this area and see what we recall of that, because this is going to be something that we do a lot here. All right, so just as a quick reminder, let's compute the total area here. All right, so the notation that we use, the area here, actually let me label that. So the area that we're going to compute is going to be the integral of our function f of x, so 4x minus x squared. Then we're integrating dx. Now, a lot of students at this level look at this and roll their eyes like, why do we have to continually write this dx thing? It just gets dragged along and nothing ever occurs with it. Well, in fact, it's actually one of the most important things there. It's telling you the variable with which you're going to integrate. And when you get into multivariable calculus, it makes a big difference. In single variable calculus, you don't really notice a whole lot there, but it does have a lot of meaning. One thing that its meaning is to help you understand what the, in this case, the left bound and the right bound of integration are going to be. So, all of you probably know that the lower bound and the upper bound that we're integrating between go at the bottom and the top of our integration symbol. What you may not be aware of is that these are functions themselves. Well, I guess not technically functions because it wouldn't pass a vertical line test, but curves. Okay, so they're bounds, all right? So the bound is x equals 0 and x equals 4. I know this is x equals 0 and not like y equals 0 because it's defined by that variable right there, okay? So all of this meshes up together because of the way we set up our approximating rectangles. And so again, this is a left bound, x equals 0. This is a right bound, x equals 4. And this is an upper bound. Okay, we're just making the assumption that our lower bound of this region, this bounded region, then, is always going to be y equals 0. Okay, now that we've made that statement, let's go through and process this as we know. This would be integrated using the power rule, and if you've forgotten the power rule, you definitely want to review it because we're going to be using it quite a bit here. And all it says to do, if you have a variable with an exponent, you will integrate it by raising its exponent by 1 and dividing by the new exponent. So then x squared becomes x cubed divided by 3. Then we're going to evaluate this new function between the endpoints 0 and 4. But I do see a little bit of simplification that can happen first. It's not a big deal, but 2 can go into 4 and make that a multiplier of 2. So I have 2x squared minus x cubed over 3 that I'm going to evaluate between 0 and 4. Which will become 2 times 4 squared minus 4 cubed over 3, and that would subtract the lower endpoint, but luckily, because that lower endpoint is 0, this whole second term really just disappears to 0. Alright, so 2 times 4 squared would be 16, 4 cubed is 64, and now we just have some fractions to worry about, so this would be, let's see, in terms of thirds, 16, I multiply that by 3, that would be Oh, I made an arithmetic error, didn't I? Because 2 times 16 would actually be 32. I fixed that. All right, so making this with a denominator of 3, so I can combine here. That should be 96 thirds minus 64 thirds, which would ultimately be 32 thirds. So the total area here under this curve is 32 thirds units squared of area. Okay, now this is something that we will be doing quite a bit, evaluating areas in this kind of situation. We'll run into, unfortunately, lots of integrals with the power rule, and in the end, the actual integration is not really all that difficult. But in the end, there's always this cumbersome work with fractions. So we're going to simplify our lives, and we're going to show you at this point how you can use the calculator to get through these next stages a little bit faster. Because if you can set up a problem, and that's ultimately what we're interested in, is you being able to set up the problem to find the solution, then you shouldn't spend the next, 90% of your time working the problem out working with fractions, because you should be able to work with fractions at this point. I think we can assume that. So we'll also run into situations where the actual integration is just impossible without more advanced integration techniques, or it might just ultimately be impossible to do. So using numerical methods in order to come up with approximations is a great tool in these kinds of situations. So one thing you want to make sure of is that you still take the time, especially on your tests, to set up the problem. So write out how you've come up with the function that you've put into the calculator, and then state that you've used the calculator to actually get the final answer. So just make sure you do that sort of thing, and you're free to use this great little bit of technology called fnint. fnint is a way that the calculator can calculate a numeric integral for you and come up with an approximation. So, for instance, it depends on what model calculator you have, what it's going to look like, but you can always change through the mode settings. So I'm in classic mode right now, just to show you what it would look like on the older model 84s or the 83s. And I'll come back and show you in the math print in just a moment. So to find this, what we do is hit the math key, and the very first menu has generally the 9th item here. If you just hit 9, it'll take you right to it. fnint. So it stands for function integral. It takes 4 inputs. It needs the function that you want to integrate, the variable of integration, because that's extremely important, and then the lower bound of integration and the upper bound of integration. So if we want to solve the previous example, what it would look like is fnint, and you just type the function in, so 4x minus x squared. That's what it would look like on the calculator often. Variable of integration is x, the lower bound is 0, and the upper bound is 4. And then what this function is going to do is, it probably doesn't use rectangles to come up with the approximation. There's like Simpson's rule, if you've heard of it. It does a much better job with approximating. It probably use something more advanced like that. But ultimately, it comes up with the approximate value of the function using one of those numeric techniques. So let's try it. So 4x minus x squared. Then x is my variable of integration. Lower bound is 0, and the upper bound is 4. It will run through the process using numeric techniques and now put an answer. Now, that answer is always going to be a decimal approximation. It's never going to be an exact answer like a fraction or a square root or anything of that nature. So what we're going to get is an approximation, 10 point, in this case, 66666, and then it says 7 in the end. If this happens to be representing a rational number, though, you can actually convert into a fraction. Sometimes. Not always, but most of the time you can. If you press the math button again, and this time the very first item, this is another little magic function here, frac. It can actually change a decimal approximation into a fraction if it's possible. So just highlight the first item, press enter. It'll take the last answer, try and convert it to a fraction if it can. And in this case, 32/3, just like we came up with before. It can save you a lot of time. Just make sure you're not using it in situations where exact answers are required and you end up with value that would be involving a square root, because there's no methods that will take a decimal value and convert it to a square root or something multiplying pi or anything of that nature. You can only take decimals that represent rational values and convert it to fractions. Now, if you're using one of the newer calculators and you have the math print turned on, it's actually really nice because when you use the FN int, you come to the same sort of notation that you would actually evaluating an integral. So you don't have to remember the order of these inputs. Although you use it enough, it's pretty easy to remember. It ends up just looking exactly like an integral, and that's how it determines all the different inputs it needs and then comes up with the approximation. And in addition, when you do the conversion to a fraction, it actually writes as a fraction as well. But that's nice, but not a necessary thing. So there you have it.